Here once again I welcome you all in this tutorial session. So here we will see the working of the magnetic stirrer, and also we will see the working of the ultrasonicator, and then later on we will talk about the filament maker, right? So this is the magnetic stirrer, right? So here this is generally used to mix the filler particles into the polymer matrix. So suppose you have PLA, right, or you have ABS. So what we do is initially first we take the solvent, right? Solvent is what? ABS solvent is acetone. So we will take the grains of the ABS and we will mix it with the solvent, that acetone, and we will take the beaker, and then also we will use one magnetic bead, because this is magnetic stirrer. So with the help of that magnetic field it will rotate that bead, right? So I think Vivek is looking for the bead. So did you find?
Yes.
Okay.
Say magnetic bead है. Suppose the downside there is a magnet. So magnet is rotating. So if you put a small similar magnet above it, so it will also start rotating. So if you put inside the beaker, the mixing will start. Suppose if I put that magnetic bead in the beaker, right? So mixing is getting started.
So usually this mixing is done for 2 hours, right? 3 hours, depending on the material and what filler we have used. So usually we have to follow the literature, right? What literature is recommending. Accordingly you can select the time, and also temperature is also very, very important. Because I want to discuss one of my case, because during my PhD I was mixing EVA and graphite, right, with the help of this magnetic stirrer. So what happened, after one day, 24 hours actually, I checked whether they have mixed or not. So I found they were not mixed together. Why? Because I didn't go through the literature properly. So I found that the temperature, I should raise the temperature also. Then only it will mix, right? So then I found that temperature value. Then because here also there is a provision to increase the temperature. Okay, so I kept around 60 degrees centigrade, and I just kept for 2 to 3 hours, and it was mixed. So sometimes these things happen. Okay, so you have to be very careful while you are using the magnetic stirrer and the filler and polymer matrix for the mixing purpose. Okay.
So generally we use this mixing. This is a kind of macro mixing, wet mixing. In that wet mixing, we use this as a macro mixing. The purpose we use here, suppose we have a resin. We have resin whose viscosity is in between 150 cp centipoise. If we suppose we have to increase the viscosity of that resin, we can add that hollow glass microsphere that we have purchased from the market. With the increase of the weight of that hollow glass microsphere, viscosity will get increased. We can mix this using the magnetic stirrer. That is a micro kind of mixing. If we have to mix it at the intermolecular level, we can use that ultrasonicator. That one is probe sonicator. The probe means, but that one is a contact type. That probe will get in contact with the liquid. But another kind of we have there is a bath sonicator. Another sonicator, we have bath sonicator. So we can use that sonicator for micro level mixing, that is mixing at micron level. So we can use also that kind of mixing, sonicator mixing. Sir, इसका demonstration के बाद the next demonstration बात sonicator. Micron level mixing, you can use that sonicator. We have two type of sonicator, that is probe sonicator and bath sonicator. The problem with the actually the probe sonicator is very accurate because it is directly in contact with the liquid. But the problem is that the probe is directly in contact with the liquid. It may react because it is in the form of metal and it may react with your liquid. So rather using probe sonicator, we generally use the bath sonicator because you take your samples in the beaker and you put your beaker inside the bath and there is no contact with the inside material in the beaker and outside the water. You can see here the bath sonicator.
Keep this beaker below. Stop this balance now.
So you just put your beaker like that and start the sonicator class.
Button is there.
Button is this side.
फ्लूइड के अंदर वाइब्रेशन और डैम्पिंग है
स्विच ऑन करेगा किसमें नहीं वो तो ऐसा करने के लिए वो है
अल्ट्रासोनिक को जो उसका सोनोटोड या जो
सोनोटोड इसमें नहीं है वैसे नहीं सोनोटोड जो उसका
कोई बेस नहीं होता इसलिए वो वाइब्रेशन जनरेट करता है
नहीं बेस तो आपने ही बना दिया ना ये क्या अभी दिखाता हूँ चलो
इसका साइज ही वैसा है ये नहीं है वो इसका तो काम किया
very simple vibrations ultrasonic vibrations
20,000 hertz of frequency of vibration
in normal water which one this one there on this side you have to do
generally we use deionized water in that bath but we don't have facility in our department deionized water so we use normal tap water but after certain time if you use normal water scales will form at the side of the container so this is prescribed to use deionized water 7 to 8 liter of deionized water we can use so the level should be the liquid should be above that level and it will work properly and you can see temperature control is also there and time control and the frequency of this working is 20 kilohertz. So this is a non-contact type of mixing. So you can see the required material is not in contact with the outside environment. But in probe sonicator, you have to put probe inside the beaker so that vibration of that probe will mix the material. Both means probe sonicator is very effective if you see because it is directly in contact with your material. Suppose beaker is there, you have to put a probe inside that beaker. Halfway you have to fill your probe in the liquid material. So probe probe will vibrate at a frequency of 20,000 hertz. So mixing will start. So that mixing will start. Here, water means mixing coming from the bottom. Water is vibrating. So that vibration is transferred to the beaker.
It is used for the
Micro mixing. This one is micro mixing. So the molecules will get in between the atoms, means in between the atom spacing. Yeah, you can use means nanoparticle also to mix here, but using this machine you can't do that. Magnetic. Yes. That will means magnet will attract your magnetic additive.
Can we measure the homogeneity of mixture?
Suppose you take initial sample, you dry it, and you do SEM imaging. And after mixing, you deposit the material or pour the material and dry and cut it and put it under the SEM imaging. You can see that the mixing is homogeneous or not. That is the only way we see.
Right after the wet state, is it possible? And the wet state is there in other than SEM?
Sorry, sir.
In the wet state.
Yes.
For example,
It is in the wet state.
so because say for example we have solicited it for 1 hour, we want to check it whether mixed or not, or homogenized or not.
So then,
Other than let's consider that
You have to trust the chemical. You have to trust the chemical.
actually, we take the literature review. We take the help of the paper, already research paper work. We do. They use the same process. They use communicator bath. After how much time they get the homogeneity? It can be 6 hours, 12 hours, even 24 hours also. One of the sample.
You don't have that much idea about the material consisting, right? So if you refer good enough related to materials and
What I was thinking that most of the time, we actually extend the mixing process for a much longer duration than actually it is required.
that is right, because that is right.
But there must be something by which we can see the homogeneity after 15 minutes.
That's why I'm saying, because we don't have that idea, right? So we just give paper of technique.
In our conduction studies, we have very different types.
Yeah.
We have the different dispersion rates.
DSAT studies that.
I have varied the time for 6 hours, then 9 hours, then 12 hours, and then up to 24 hours.
What was the observation?
For 24 hours, I got the better dispersion.
No, but I have read somewhere that there is actually an optimization value, and beyond that, it starts evaporation.
Yeah.
After 24 hours, is there any kind of say homogeneity maintained, or when we achieve the same homogeneity?
I have used ultrasonic process. And for 24 hours, I got the best result. Compared to carbon.
Okay, this I improve after 12 hours.
There is high dispersion of the nanoparticles.
But they cannot keep on improving infinitely. So there must be some peak, and after that,
Cost to
You can go to the next one. Because we have
the next 1.1 lakh rupees. This machine cost. That bath sonicator cost around 39,000, and that mixing
3,000 to 4,000.
4,000 to 5,000 hardware.
this is only 39,000?
39,000. Yes.
ये साइज पड़ ना इसका भी
इसका छोटे वाला 10,000 वाला
बहुत छोटा मिल जाएगा इसमें तो आपको 10 20 में मिल जाएगा. You will find it.
ये इफेक्टिव है और मीन्स वेरी इफेक्टिव दिस वन इज, बट इट इज अ कॉन्टैक्ट टाइप. सो
तो सेम ही
कंट्रोलर वाइज देखे तो ये पल्स मोड है और कंटिन्यूअस मोड. लाइक पल्स मोड for 2 seconds the vibration will happen and 3 to 5 seconds it will stop so that cooling can happen. हाँ ये भी यूज कर सकते हैं. So that one is the probe and we have other probe also have a smaller diameter and placing के लिए since we have small beakers so we have customized the stand so that it get in contact.
And also we can vary that probe size also. Right?
Probe size, yes, we have two.
We have two types of probes.
So we put here our material and we should. दूसरे लग मतलब connected. Chemistry environment. People who are working in the material field, they definitely have this kind of sonicator, probe sonicator. In the bio lab also, in the chemistry department, they have this kind of probe sonicator. So, how to start this? This is the power mode and this is the frequency you can see here. 25 kilohertz frequency. At that frequency, the probe will vibrate, and this is the run time and off time. So I have to set it, and this one is a pulse mode and continuous mode. Pulse mode means for particular time it will start and for some time it will stop. We use this just to cool down the probe because it will get heated if it will continuously vibrate. So pulse mode we use here, and the timer mode. Suppose 20 minutes we enter. Run time, on time 8 seconds. This one is in minute, this one is in second. So on time 8 seconds it will work. I should reduce it to 2 seconds. Enter. And off time 5 seconds. Enter, and I should put it. See, mixing getting started. 5 seconds off and 2 seconds mixing. I can change it, depends on my material. So after mixing it with magnetic stirrer, so you get uniform mixing of the material. Then now you have to go from macro mixing to micro mixing. So you can use this.
You use in steps.
Yeah, stepwise you have to use. Either use it with your hand, like mix it for macro mixing, because if you pour powder or some additives in the liquid, it will form at the top surface only. You have to mix it to get it uniform. After some uniformity will be there, you have to put it. You can use it under the probe sonicator for micro mixing. So this kind of thing is there. So with that mixing only, we mix resin with glass microsphere and we put it in DLP 3D printer machine, and we printed dog bones. Yesterday I showed that sample. We prepared from that probe sonicator and we printed it with DLP. That is a composite material. We used for application wise, we printed that for printing low dielectric constant material to use it in electronic application. Because in electronic, there is a conductive tracks is there. Below that, there is a dielectric material is there. So for ISRO project, we are preparing for dielectric material and conductive material. So this is the machine.
Some constant temperature.
Temperature, here temperature will vary. Temperature will getting increased, means if you increase the time of vibration. Yeah.
This energy is ultimately getting it.
Vibration energy getting converted to heat energy.
For example, if at all the resin has a limitation,
Yes.
like it should not
So it may
cross
affect the,
40.
it may affect.
It will change the property also sometimes.
Will we able to find the temperature on the screen?
No, not here.
No, but that option is not available in this sonicator.
In this.
But it might be there. Okay. If you ask the manufacturer, they can just make for you that kind of.
Okay.
We have another one in another lab, but this is not having that.
Since we are in from mechanical background, we have contacted with other people who already used it from years. So they said that if you have to use probe sonicator, you put ice around it, so that temperature shouldn't get increased. So that is why we don't generally use this probe sonicator. We use spark sonicator for mixing. And this one is also contact type. Mixing is high, definitely mixing is very much high. Uniform mixing will be there, intermolecular mixing will be there, but the temperature, it will change the property of the material. Means high, if temperature will increase, your viscosity will get decreased, and temperature may change the property of the material. I was mixing resin. That initially resin was little bit yellow, but after mixing for 3 to 4 hours, it become brownish shade because of heating. So mixing time means on time and off time is very important in probe sonicator. Like if you use 10 second or 20 second continuously, it will produce much heat. If you use it for 2 seconds, on time and off time is 10 to 20 seconds, it will reduce the temperature also. But you have to, your sonicating time should be high, so that the on time can be high. Like 2 seconds, you have to put it for 1 hour. So this is the mixing. Any question regarding?
And these are the mechanical tests. Apart from that, we can test for their thermal degradation behavior. We can test for their dynamic mechanical behavior, right? And there are other non-destructive tests are also there. For example, if you want to characterize the voids or the structural changes after application of certain load, you can do the micro CT scanning of the composite material components to understand the internal structure of the composite material. So I will start with the from the basics, okay, because these are again very important. Especially testing of the composite material is easy, okay, but analyzing the result is very important. How you analyze the results and what is the conclusion after analyzing this particular result is very important. So we will start from the basic, the simple mechanical test, that is tensile test of the composite materials. So generally for the fiber reinforced composite materials or even the fabric reinforced composite material, we carry out the tensile test according to generally this D3039, ASTM D3039 standard. And in this particular, according to this particular standard, we take a sample dimensions 250 mm by 25 mm, right? And cross head speed is 2 mm per minute. For
So what is this cross head speed?
cross head speed means what? So if you look at the principle of the this testing machine, it is tested based on constant rate of extension. So what is the rate of extension, rate of application of load on this particular composite material? So here, So you see that this is the bottom and top jaw in which the sample is gripped, and at this bottom jaw is fixed, whereas this top jaw will move, and at what rate this top jaw will move, that is the crosshead speed.
I think that is same rate. I think.
It is variable.
It is
It can be
variable.
varied.
It can be variable.
But in this particular standard, that is fixed.
In this case, we generally test, according to this particular standard, we test at 2 mm per minute. We can vary this test because in case of yarn, in case of textile yarns, the speed is very high. In case of other fabrics, the speed is again different. But in case of composite material, we test at very slow speed. So we call it as a quasi-static test because this speed is so small that it is approximately constant. So therefore we call these tests tensile or flexural at such a small rate. So we call them as a quasi-static tests.
Taking much more time.
Yes, it take not too much time. Especially the tensile test, it will not take more than 15-20 seconds. It will not take more than that. It will test. It will be the sample will fracture within 30 seconds. There is no problem. But in case of flexural test, it will take time. Flexural and compression test, it will take time. In case of flexural test, we have two different type of flexural tests. So you must be aware. One is 3-point bending test and another is 4-point bending test. So here is one picture which is shown. This is the example of 3-point bending test. So here you see that there are two bottom support on which the sample specimen is placed, and this third point, right, which is attached to the cross head, right, it will move at certain rate, that is 2 mm per minute here, and it will bend this particular composite sample until it fails. So here one more terminology, that is span to thickness ratio. So what is this span to thickness ratio? So what is span? Span is nothing but the distance between these two bottom supports. What is the distance between these two supports is called as span, and
Thickness of the specimen.
how much is your thickness of the specimen? So if you look at the ASTM standard, this D7264, various span to thickness ratios have been given: 16, 20, 32, 64. And these span to thickness ratio has to be decided based on how much is your thickness of the sample, and you have to choose it in such a way that the sample should fail at the tension side, that is from the bottom side. So when this specimen is loaded in the 3-point bending mode, the top side experiences the compression, whereas the bottom side experiences tensile load. And the specimen should fracture from the bottom only. If it fracture at the top, this test is not considered okay. So the sample should the specimen should fracture from the tension side only, right? And you have to choose the span to thickness ratio based on that. That, for example, if your sample is very small, very thin, for example, 2 mm thickness. If you are choosing 20 span to thickness ratio, so 2 into 40, it will be simply 40 mm. So if the span is only 40 mm, so it will be very difficult for such a small sample to fail at the tension side. So in that case, you have to choose different span to thickness ratio. So this span to thickness ratio is very, very important, and this is solid sample. So then it is more easy for one to decide the span to thickness ratio. But if it is a spacer composite, which I have shown you yesterday, so in that case again the choosing the span to thickness ratio is again difficult. So you have to use some other standard for that particular case for testing. For spacer structures, the test standards are and the third test is impact. So in case of impact, as I said you that there are 3 different impact tests you can perform. One is isolate impact test. where you place the sample vertically and then the impact is the hammer impacts on the edge of the composite material, right? The second is in case of in plane impact, so we place the sample composite specimen horizontally and the impact is made on the edge. So that is again the Charpy test, which is called as Charpy test, and that is also in plane impact test. And the third one is the out of plane impact test, that is drop weight impact test, where we place the sample right, and from the impactor hits on the composite specimen, and we measure the impact.
Choose the impact type test.
Yes, there is a guideline. So based on what is the mechanical performance required for particular application. For example, in case of automotive composites, so there are guidelines. For example, if you want to use any composite material for the dashboard, there are standard guidelines that how much should be the tensile modulus of this particular composite. It should be around 2.5 GPa tensile modulus. For flexural tests, there is again a guideline for particular components. Flexural strength, flexural modulus. Again, for the impact test, there are standards. So if you and suppose if there is some different type of composite material, for example, you want to use it in applications where the bending load is applied, or suppose compression load is being applied on the composite material. So in that case, you have to go for those particular type of tests. So again, one more. This is one of the again interesting tests you must be aware. This is the bearing strength of the composite material. So this bearing test is performed to understand the strength of the composite material under pinned joint. So because any composite material you are taking, during fabrication of that particular composite material, in actual application, you have to join it. And for joining, we use generally the pinned joints. And using this particular test, we can characterize how much is the bearing strength of this particular composite material under pinned joints. So there are various types of pinned joints. So you can have single pin, you can have double pin, you can have threaded bolt test, you can have this test without threaded, you can have this pin. So there is again this ASTM standard, that is D5961, and according to this particular standard, you have to prepare the test specimen and you have to prepare the fixture to hold this composite material. So this is the fixture, right, test fixture, and this is the specimen which is held with the help of here one pin, and you have to hold this particular top side on the top jaw and the bottom, this specimen in the bottom jaw. And similar to tensile test, at certain rate, for example, you can take 2 mm per minute or any other rate, and you have to check how much is the load experienced by this particular composite material.
Are these facilities available in the?
Yes, we have fabricated our own fixture. It is simply the fixture. There is nothing else, and you can also fabricate your own fixture. There is no problem. So if you look at this particular fixture, you can prepare the fixture using metals also, or you can prepare this fixture using composite materials.
For loading means again the tensile machine will be used, right?
Tensile UTM, simple UTM machine.
And do you have the facility for all these 4 types of tests, tensile, flexural, and
we have facility for tensile, flexural, but we do not have right now for the impact test.
okay?
And
And what about the bearing standard?
Low velocity impact.
So we have that drop weight impact test, but not the ISOD or Charpy impact testing facility right now here. So this is again one of the interesting tests, and I will show you how the next test is thermogravimetric analysis. This you must be aware about this test. This particular test is carried out to understand how your composite degrades with temperature. And here is the just one example we have given for any that for example if it is a cotton epoxy composite or a glass epoxy composite or basalt epoxy or Kevlar epoxy type of composite, you know, epoxy generally degrades around 300 degree, 250 to 300 degree degrades. But since if you want to find out, suppose let's say you want to find out the behavior up to certain, for example, more than that epoxy degradation temperature you can carry out, and it is generally we do this TGA under nitrogen atmosphere. Why? Simply to avoid the oxidation of the sample. Otherwise, it will degrade earlier. In nitrogen atmosphere, the oxidation will not take place and it will degrade slowly compared to your without nitrogen, and at certain rate. So this rate you have to decide. For example, it can be 10 degree per minute. You can have the rate of increase in temperature within that particular chamber.
Does this rate affect the test result? Or
Yes, this rate affects the test results because test will give you how much is the change in the weight of the specimen with temperature.
with respect to yes.
So this rate again it influences the change in the weight. Suppose the rate is higher, for example 30 degree per minute. So the composite may degrade earlier. And the next again one important test is water absorption test. If your composite is, let's say, natural fiber reinforced composites, in that case you must test it for the water absorption test, because natural fibers are hydrophilic in nature. They absorb the moisture from the atmosphere, and once if they absorb the moisture, it will directly influence the interface with the matrix, and it will lead to change in the it will lead to decrease in the mechanical performance. And this is the one of the test known as ASTM D570 using this particular standard. So how the sample is tested using this standard is, you can simply take the specimen, right, take the weight of the specimen and simply dip in the water. You can use tap water or you can use some distilled water also, that is up to your choice. And after every 24 hours you have to remove the sample, you have to remove the excess water using tissue paper and take the weight of the sample, again put it in the water, again check it until you get no change in the weight, until the saturation takes place. And then after saturation, so that is the saturation time, so that may be for some samples it may be 1 or 2 days, for some sample maybe 30 days, 40 days. So it is a long test. Suppose it is, for example, we have done using for the cotton epoxy composite, it took us 30 days. Sometimes it takes more than that. You can test this particular natural fiber composites or even the glass epoxy composites for this water absorption test with water at elevated temperature. You can simply take a kettle, right, use the hot water, right, and you set the temperature of this particular kettle and you put the sample, and after every 24 hours you measure the change in the weight. So you can understand
in that case how we will maintain the temperature of the
so you have to take a kettle with temperature, you can controller, temperature control. So in that case you can do it very easily. And if you want to test, let's say, change in mechanical performance after water absorption, so for that you have to use simply what, let's say you want to test the tensile properties or flexural impact properties. You take a specimen of that particular size and you put in a water and do this experiment, means checking the weight after every 24 hours until the composite saturates, and then after saturation you simply test it and you check the mechanical performance. So in that case, so in this way you can identify, you can say, you can characterize mechanical performance after saturation with
so
the water.
what application this test is very important.
So for the outdoor applications of the composite material, because today a lot of people are talking about the natural fiber reinforced composites, and they are saying that these are the green composites because natural fibers are there, even though the matrix is synthetic. I mean the polymeric matrix. So for the outdoor applications of such composites, you need to do this particular test. And But one more important thing is that you will experience, if you do this particular test, you will experience that if you change the specimen size, your results will vary. Suppose you are taking a 5 by 5 centimeter sample and you are checking the water absorption, and if you are taking a little smaller sample or little larger sample, for example 10 by 10 centimeter sample, you will get different results, completely different results. And you therefore you have to choose only one size of the sample for matlab if you are doing multiple tests, right, for the different type of samples, so the size should be same. Otherwise the water absorption result will be different. And so if you look at this particular plot, this is the plot of fiber volume fraction, effect of fiber volume fraction on the tensile strength and modulus of the composite material. So once you have got these results of the tensile strength and modulus, comparing the results of the material becomes difficult, when you have simply the results in the, let's say in the Newton, you have just breaking load in the Newton, so you cannot compare it. So therefore you convert it into the stress form. But even those values are difficult when you want to compare with some other material. So therefore you can calculate the specific tensile strength in that case, that is the tensile strength divided by the density of the material, or you can normalize it by dividing with weight of the composite material. So it will give you more appropriate idea about the mechanical performance of the composite material, and the results will become comparable. Similarly, in case of flexural strength or any other test, so you should try to find out the specific mechanical properties, and then only it will be more easy for comparative analysis. In case of tensile tests, look at this particular composites. These are the composite specimens fractured under tensile loading. You see that how these particular composites are fractured, whether it is a straight line of material separation or is it a wavy. So this is also again approximately straight, this is also approximately straight. Or sometimes you see the composite material fractures with waviness at the line of separation. This will give you an idea about how your material reacts to the tensile load. Right, and at different speeds also you can carry out this particular test and identify this particular material behavior and why this. So there can be various reasons why the material is separated exactly approximately at the straight line and why it is not separated with, let's say, waviness. So that is again one of the points which should be investigated. Under this flexural tests, for example, you see, as I said you that under 3-point bending, the top layer experience the compression, bottom layer experience the tension, tensile load. And if you look at this particular composite material, this is the cotton epoxy composite and this is the polished epoxy composites. So this is the recycled cotton epoxy and this is the again recycled polish. You see that cotton epoxy composite, you can see the fracture of the material at the tension side, but in case of polyester there is no fracture. There is no fracture, and the reason behind this particular thing is, the polyester is more flexible. It has more elongation at break, around more than 20% elongation at break. Polyester fiber sometimes have. So in that case, the composite material you can get more elongation at break, and therefore it will not fail. So when you are designing a composite material, even you may think that it is epoxy, so it should fracture, right? But it is not fracturing. So if you are engineering any composite material, deciding the fiber material again is very crucial based on what is the application of that particular composite material. This is the same image. Again, you must be aware about the scanning electron microscopy of the fractured specimens, right? And we try to understand how effectively your how effective is your the how much is the fiber matrix interface, and you can find out how your fibers are actually fractured in the composite material, whether there is any fiber matrix debonding or fiber pull out. So fiber pull out is an indication of poor fiber matrix interface. So
Do you have SEM facility, sir?
yes, we have a SEM facility at the central instrumentation center. Yes. This is the result of water absorption of cotton epoxy and polyester epoxy composites. So in the water absorption test, we generally measure these two properties. That is equilibrium water content, that is how much is the maximum water this particular composite can have at the time of saturation, and another one is the diffusion rate. At what rate your composite is absorbing the water. So these are the, again important. And as I said you that if you see that when natural fiber absorbs the water, it swells, and because of this particular swelling, it will directly lead to you can say it will directly affect the interface between the fiber and matrix, and therefore the mechanical performance of this particular composite material deteriorates. So you see that again.
So after conducting this test, we can again go for the mechanical test.
We can go for. So we have done it. So we have done it for this particular composite material. So you see that for the dry cotton epoxy composite, the material fractures under flexural loading, but after water absorption, it becomes flexible. It becomes flexible, and we do not see this crack at the tensile side of the particular composite material. So this is the result of this bearing response of the cotton epoxy and polyester epoxy composite material. So you see that how we have analyzed this particular result. So when any composite material fails under this particular bearing load, it fails with different types of failure modes. Let me tell you first. So the material may fail in a bearing mode, or it may fail in a cleavage mode, or net tension mode, or maybe shear out, or maybe the tear out. So these are the various failure modes. You see that. So here you can see the shear out mode. Here you can see the net tension mode. So why this particular composite has failed in the shear mode, or why this composite has failed in the net tension mode? Because you see that bearing or shear out mode is more preferable, because it is the reinforcement is actually taking the load, and it will sustain that particular joint, right? And these are not good actually, the failure modes.
This is not desirable.
This is not desirable. So how to improve the performance in the bearing? So you only by changing the reinforcement structure you can enhance these are the fiber reinforced composites, simple fiber reinforced composites. If you go for fabric reinforced composite materials, it will give you more bearing strength, and it will fail majorly in the bearing mode, and not in this cleavage or net tension or tear out mode. Because of the reinforcement, as I shown you yesterday, the oven fabrics, you have interlacement in the warp and weft direction, right? And because of this interlacement, it will not allow that particular specimen to break in the net tension mode. So if you look at this analysis of this particular test, you see that how we are analyzing it. On the x-axis we are plotting the strain, on the y-axis we have this bearing stress, and the other y-axis we have rate of change of load with the strain. So if you look at this particular plot, there are generally 4 regions. So this is the first region, so this is the stabilization region. followed by the elastic region, where you will get a straight line of this particular bearing stress and strain curve, followed by this pre-mate tension zone, where the actually matrix crack extend, and finally the composite will fail in the net tension here, right? And this red plot, it shows the change in the load dp by dl, there is change in the load per unit change in the extension. So how this particular joint is experiencing the load. So you see that up to certain point it takes the load, but after that better, you can say bearing strength, and they are failed in almost in a shearing mode, whereas these are cotton and jute epoxy composites, so therefore they are failed in bearing mode. Thermogravimetric analysis, so these are the typical plots you see in the TGA analysis. One is the weight loss with temperature curve, and another is the derivative weight loss. These two plots you get. So this plot will show you, so you see that on the y-axis you have weight, on the x-axis you have temperature. So with increase in the temperature, how much is the reduction in the weight of the composite. So 100 means the initial weight of the composite material, and with the increase in the temperature, how your composite is degrading, and at what temperature actually it will show you the very high change in the temperature. So this is the region, this is the temperature region, for example this 300 to 400, where we can see the maximum reduction in the weight of the composite material. So you can say that our composites, this particular composites, are the cotton epoxy composites, these are thermally stable up to 300 degrees centigrade. You can see that there is a very, very small change in the weight of the composite material up to 300 degrees centigrade, and they are thermally stable enough up to 300 degrees centigrade. If you look at this derivative weight loss, so this particular plot you will get on the x-axis temperature, on the y-axis percentage change in the weight per unit time. So you see that again up to 300 degrees centigrade, the change in the weight per unit time is very, very small. The rate is very, very small. But after this particular temperature, between this 300 and 400 degrees centigrade, the weight, so the rate of change in the weight is very, very high, and therefore only you can see that the reduction is very high in this particular temperature range, 300 to 400 degrees centigrade.
Weight loss occur due to the erosion of the component?
Degradation of the materials.
Because of
In
the
which form? Degradation? In which
melt
form?
and vaporize, right?
It degrades. So degradation means what? You can say it can melt. It can, for example, if it is a polymer, it will melt and evaporate. And at the end of the test, the component which will not evaporate, they will remain as it is, as a ash. So this is what here. So it will remain as ash. So it will not be zero weight. There will be certain component which will remain as it is, and therefore it will not be zero. So this is called as final the ash of this particular composite material or any polymeric material that you are testing for this particular test.
In case of DTG, up to 300 degrees centigrade it becomes stable. The rate is stable, but and there is a downward curve. And again it gets pulled back and then it becomes stable. So
Right. So this may be because this is because majorly if you see that the weight is reduced here, but this may be because the ash content, maybe because of the ash and in this particular case,
whatever the residues remain,
remains.
it reflects
It reflects. That is what
stability after I think 500 degrees centigrade later on.
Yes, this is what.
It initially becomes a negative derivative and then again it
becomes positive. Yes. This is the typical curve you will get in every case.
Yes,
In every case you will get this.
The nature remains same.
Nature.
Only the temperature difference.
Difference will be there, but the shape of the curve will
Yeah.
be same.
Yes.
So I have one note, sir. Whether you said that it is stable up to 300 and it is coming down almost 20 rate. So whether that is the melting point of the composite that we are testing, 300 degrees Celsius.
Here,
Yeah.
Major weight loss happens from 300 degrees centigrade to 400 degrees. Major decomposition of that material. Yes, sir.
so at this particular, this is the on-set temperature. From this on-set temperature means what? The temperature from where actually the sudden change in the weight of the material takes place. So this is what it is, and we also measure the 5% weight loss temperature.
Yes.
That at how much temperature there is a 5% weight loss. So look, there are so many things people show in the research papers, right? But we have to see what exactly is required for our application. Whether, for example, you are using this composite material for the railway application, for example, or aerospace application, or any other material. What is your requirement? What
We
is
also
your
having this
requirement?
facility, sir, in our institute.
TGA analysis it is not available. It is not available in the institute.
In certain cases, the polymer fabric which we are using, that may be reactive to the skin. How long you are wearing that, just like epoxy or terylene, that may not be suitable for a particular kind of persons. So there is some.
These are composite
there are
materials,
some,
but not fabrics.
okay.
Sir,
There is some test available which can judge that skin irritation test or something like that.
Yes, these tests are available, but they are for the fabrics. These are
In our institute, that tests are available.
no, these tests are not available. But you can, but these, this is actually the thermobiometric analysis of composite material. You can do this TG analysis of any material, and let me tell you once again that this. So depending upon the application, we have to decide that how much up to how much temperature this particular material is stable. And let me tell you one more important thing is that we say that we can use this epoxy composite etc. But we have to, again, one more thing we have to analyze is what are the emissions during the burning of the composite. For example, let's say you are using this composite in a train, and suppose there is a fire accident takes place. So if this particular material is generating dangerous smoke, then it is highly hazardous. So you have to. So there are certain.
Devolved gas analysis. Devolved gas analysis we have to do.
Yes.
We have to take the out from the DAC and we have to analyze the gases which is coming out of the
But there are today you have some TGA, this thermogrammetric analyzers equipped with gas analysis.
Yes, sir.
Integrated machines are there, so you can analyze the gas, and based on that you can do this. So another one more test here is the compression test of sandwich composite structures. So you can do this particular compression test for sandwich composites if your application is like that. For example, you are using honeycomb composite or any sandwich composite in the flooring or any such application where it is experiencing the compressive load. So for that particular test, for that particular application, we have to do this compression test. And again, the test standards are different. ASTM D365 and 364. These are the two standards basically for the compression test of the sandwich panels. And in this particular test, we actually measure how much is the energy absorption of this particular composite material, and how this particular composite material is actually failing. So I will show you one plot I have with me. So let me show you that. So you will get an idea about how this. So So you look at this particular plot. So this is the again same honeycomb structure, honeycomb composite material under compression load. If you look at this particular plot, deformation, force deformation plot, you will see the 4 regions. First is the elastic region, where this is the your Hookean region, where you will get a straight line, right? Then followed by the yield stage, followed by the yielding. Then there will be a region where approximately no change in the load will take place. So your material deforms, but the load remains approximately constant. And then followed by the compaction stage. Compaction stage means the densification of the material will take place, and then therefore only the load experienced by this in this stage is more, because the densification has taken place. So this is the typical plot you get in the compression test of this sandwich panels, right? So and you can find out the energy absorption. So you can find out generally for the comparative analysis we do this, we find the energy absorption within the Hookean region, within this where we get a first peak.
Okay.
So we find out
Maximum.
the area under this particular curve up to the first peak, and this is, we find out the energy. Again here, finding energy is very easy, but analyzing of the energy for different type of specimen sizes, right, it is different. So for that we have to measure the specific energy per unit volume or energy per unit density. So these type of composite materials, honeycomb, as I think I have shown you this or not. So this honeycomb, these are used in the helmets because they are very high energy absorbing materials. So you see that this is the hemp fiber. So this is the honeycomb fabric made out of the hemp fiber and their composites. And this is the Kevlar. This is the honeycomb fabric made from the Kevlar and converted into composite material. So that's all about this this characterization of the composite material. If you have any doubt, please ask.
BSc analyzer is working or
This I don't know exactly, but maybe in the working.
And what is this question?
This is TGA, thermogrammetric analyzer.
TGA.
TGA. Any
Where
doubt?
we put the sample inside this
So-
machine?
The chamber is here. So in this particular chamber we place the sample.
If I need to find the melting point of the composite material, I will put it in DSC and I will heat it up to maybe 600 degrees. So suppose it is epoxy resin and a fiber, glass fiber. So whether it will melt separately, whether I will get 2 peaks or it will be 1 peak.
No, look, the thing is that the epoxy resin, after curing you cannot melt it. After curing you cannot melt it. Let me tell you a very important thing. You may be buying any epoxy resin from the market. How to find out the curing temperature of the epoxy resin? So you can find out this curing temperature using the DSC.
yes.
You simply take the epoxy resin and the hardener in proportion of this epoxy resin, mix it and do it, place it in a DSC. You will get the downward peak. That point is your curing temperature of that particular epoxy. People generally do mistake. What they do, they generally take any epoxy resin, they mix it and simply cure at any temperature given in any research paper. But that is wrong. So you will not get a good mechanical performance if you do like that. So you have to do DSC, then only you will get a correct curing temperature for this particular epoxy. Right. Okay, thank you very much.
Thank you.
Thank you very much.